We've worked with one sample hypotheses using both the t-test and confidence intervals. Now let's work with two sample hypotheses. What we want to do now is compare two groups, perhaps an experimental group with a control group. And the way we're going to go about this is obtain a random sample of subjects and then allocate those subjects to the two groups in some random fashion. And at some point we'll discuss this whole process of randomization. It's not as trivial as it seems. So we're going to allocate our subjects then to both the experimental group and the control group, and we're going to control all extraneous variables so that the only thing that matters is membership in either the control group or the experimental group. And then what we're going to do here, just for review, just very briefly, is make sure that we understand the variance of the difference between the two means. So up to this point, we've just had to work with the variance of a mean. Now we have to deal with the variance of the difference between two means. And then what we want to do is test for the difference between those two means. And in this first example at least, we will have a two-tailed test because we don't know whether the control group or the experimental group is going to end up with a greater value. So our null hypothesis is simply that mu sub c is equal to mu sub b versus the alternate that mu sub c does not equal mu sub b. And of course we can rewrite those hypotheses as mu sub c minus mu sub b is equal to 0 versus mu sub c minus mu sub b is not equal to 0. And that's nice, right? Because then if you think about our one sample hypotheses, we had an experimental, we had a theoretical value for the mean, namely c or 0 or whatever. Here we're doing precisely that. So we're really not doing anything different from what we did in the one sample hypotheses. And then our test statistic is simply x sub e minus x sub c divided by the standard deviation of the difference between those means. And here you can review this at your own leisure. But here's the proof for how we get to our computational form for the standard error of the difference between those two means. And then, of course, the question becomes, how do we, what then is our best estimate of that? And that's, we're going to use the pooled standard deviation. We don't have to worry about that very much because in both SAS and R, it's going to do that for us. So we're just going to do it here in an example computationally. And then you're going to simply rely on R or SAS to give you, or even Excel to give you the correct answer. So the standard deviation of the difference between two means is then the pooled sample variance divided by its sample size, and that's for both groups. And then we take the square root of that. So it's pretty straightforward. And this turns out to be a better estimate than how you would typically compute it. Simply because in a very real way, you're just taking the average of those sample variances. So then here's our test statistic, and here it's important to note what's gone on with the degrees of freedom. Notice in the one sample hypotheses, we had simply the degrees of freedom was n minus 1. Here, however, we're estimating two means, and you can see that in the formulation for the test statistic up above. X bar minus x1, or x bar sub 1 minus x bar sub 2, minus mu sub 1 minus mu sub 2. So we're estimating two population parameters here, mu sub 1 and mu sub 2. And for that reason, we have to subtract 2 degrees of freedom. Let's look at some data that we have here. These are data for foreleg lengths and hind leg lengths in deer. We have 10 deer. Perhaps we've gone to a deer check station and we make these measurements on the first deer that come in. So the first column is hind leg length and the second column is foreleg length, and you can see what the values there are in centimeters. And here then our hypotheses and our test statistic, and we compute x bar sub 1, and that's 144.7. X bar sub 2 is 141.4, and then um, the standard deviation of the difference between the means is 1.6. Our test statistic, our tabled value is 2.101. And you realize right away that our computed t-value is not greater than the test statistic, than the limit, right, if you want to think about it in terms of those confidence limits. So it's not greater than, so the limits contain our value, right? 1.978 is less than 2.101. Therefore, we're not going to reject the null hypothesis. And that's not a very pleasing result because from vertebrate biology, we know that mammals and reptiles and most vertebrates, amphibians as well, have hind limb dominance. That is, the back legs are bigger, longer than the front legs, and that's all about the physics of locomotion and so on. But so we know that there's a problem. So why is it that this test gave us an answer that is theoretically at least incorrect? And the answer is that we ignored a very important point. That is that the forelimbs and hind limbs of these animals are not independent of one another. Each foreleg was firmly attached to the same body that contained the hind limb. So a bigger animal is going to have longer legs than a smaller animal. So there is some sort of covariance that exists between these. And that goes back to, if you think about it, to our rules of expectation and variance. The variance of a sum is equal to the sum of the variances plus twice the covariance, unless, of course, the two samples are independent. And we don't have that here. So what we've done is ignored that covariance term, and as a consequence, we have the wrong answer. So we need to treat this in a slightly different way. And in order to do that, we're going to treat it as a paired sample t-test. Recognizing that the forelimbs and hind limbs are attached to the same animal. So now we have our 10 animals, and instead of looking at the individual leg lengths, we're looking at the difference between those limb lengths. Now our null hypothesis is that mu sub d, the mean difference, is equal to 0, versus the alternate that mu sub d is not equal to 0. We're going to use an alpha value of 0.05. Our t-statistic now is d bar minus 0 divided by the standard deviation of the difference between, or of the means, or the standard error of the mean. Our mean difference is 3.3 centimeters. S sub d bar is 0.966. And when we compute the t statistic, it's 3.4132. And compare that with the tabled value, and this is a two-sided test again. But we now have only 9 degrees of freedom instead of 18, so the tabled value of 2 is 2.262. Our value of 3.4132 is far, far outside those limits. It's much more extreme than 2.262. Therefore, we're going to reject the null hypothesis. So this is an example of a situation in which you have to think very carefully about what it is that you're doing, and you have to think about covariance and independence of samples. And in this case, we get a result which conforms with what our theoretical expectations are.